right? Any of these terms in our orbital angular momentum operator are going to be suspect to Heisenberg. So what happens if we look at the commutator between those individual operators? So for example, if I look at the commutator between the y dimension and the x dimension, okay? And so recall this commutator, right? We go Lx, Ly operate on psi minus Ly, Lx operate on psi. And if these are equal to 0, there's no uncertainty. But if they're equal to non-zero, there is an uncertainty. And as it turns out, the commutator between Lx and Ly is given by I h bar Lz, which is kind of cool actually, because I'll remind you, so recall in just our two-dimensional standard translational Heisenberg uncertainty model, right, where we just looked at position and linear momentum. So recall the commutator between those two was IH bar, right? So it's kind of cool that this works out to be IH bar LZ. And so what this means is if I try to specify with arbitrary precision the angular momentum projected length in the x and y dimensions, I will have uncertainty in the z dimension. Well, what do you want to bet is going to happen if I switch those dimensions? So if I look at now the commutator between Ly and Lz, if you're saying IH bar Lx, then you're getting it. So IH bar Lx. So now, if I try to specify with great precision the projected length of orbital angular momentum in the y or z dimension, I have uncertainty in the x dimension. And of course, finally, if I do this for the last pair, which would be Lz and Lx, of course, I'm now going to have uncertainty in the y dimension. Okay? So how the hell are we going to do this, right? How are we going to specify this particle's total orbital angular momentum if by trying to specify any two dimensions, I then get uncertainty in the third dimension? Okay. Well, the answer is that if we specify one specific dimension, which we're going to give special treatment to the z dimension, and that's just arbitrary. We could have picked x, we could have picked y. But as it turns out, as we keep going down the rabbit hole in this class, we're going to give special treatment to the z dimension. And that's just based on this right-hand rule, okay? That if I'm rotating in the xy plane, I have angular momentum in the z dimension. But if I pitch this thing, right? So if I go back and draw my coordinate system, y and x and z, well, if I allow this to pitch, okay, look, this vector is still going to give me some projected length on the z dimension, okay? Of course, there's going to be projected length on the other two dimensions. So we're going to give special treatment to the z for one. But also, what if we give special treatment to just this total magnitude? So remember, if I go back to our vector review, remember the one that's going out in that angle theta phi, that's going to give us our total magnitude of those two projected lengths. So what if we try to specify with great precision the magnitude? Okay, well, that becomes pretty cool. And so what we get, so to do that, right, so first of all, to get the total magnitude, I think this is why I have so much extra space, all right? So we recognized that when I look at the angular momentum here, it was Lx, okay? And I'm going to drop the vector ijk because we recognize that that is just meant to signify that it's a vector in those specific dimensions. So if I want to know the total magnitude of this vector, then in vector math, what I do is square this operator, okay? So total magnitude is given by the following: L squared, which is going to be Lx squared plus Ly squared plus Lz squared, and this is going to create a Pythagoras triangle, which is very cool, and we're going to see that coming up. And also, I'll just kind of supply for you this value here. When we go through all of this, it's a pretty cumbersome result. It equals h bar squared over, or h bar squared times the Legendran squared. And recall that Legendran squared, right, is that big nasty 1 over sine squared theta, et cetera, et cetera, et cetera. Okay. Well, as it turns out, so here I've got that all summarized right here. If we now look at the commutator between the magnitude and any one dimension, x, y, or z, then we have no uncertainty, okay? Which is awesome. So therefore, and right, we have no uncertainty because that equals 0, okay? So therefore, although we may specify the magnitude of angular momentum and any of its components, if, and here, this is where we're giving special treatment to LZ. So we noted here that this could be X, Y, or Z, but we're going to choose Z for arbitrary reasons. So if LZ is known, then it is impossible to ascribe values to the other two components. So that's kind of saying what we discovered here, all right? And I probably should have put another line here. But now, if LZ is known, and we know the total magnitude, then we no longer have a Heisenberg uncertainty principle situation at hand, okay? So how does this play out? All right, well,